Welcome everyone. Let's have a look at left and right hand derivatives. As we learned, for a limit to exist, we need to check it from the left and the right side, and if these limits are equal, then we will say the limit exists. The same for the special limit we have for derivatives. When we check it from the left and right side, if these are equal, we will say our limit, our derivative exists. When we check the limit from the right side, we call it right-hand derivative, and when we check it from the left side, we call it left-hand derivative. Let's see an example. Fx is given to us, a piecewise function, and the derivative at point 1 is asked. First of all, if the point was not 1, we could have just used the right equation for us, right? But since it is 1, we need to check the limit from the right and the left to talk about the derivative, of course. So fx minus f1 over x minus 1, which is equal to, first let's figure out what f1 is equal to, negative 1 plus 2, which gives us 1. So you limit, push the 1 from the left side, which is lesser than 1. X squared minus 2x plus 2 minus 1. This is over x minus 1. And this is equal to x approach to 1 from the left side. X squared minus 2x minus 1 over x minus 1. My numerator is x minus 1 squared. No, it is not. Wait. Oh, yeah. Wait. The plus 1, right? Okay. Now it is. All right. We wrote it wrong here. So therefore, this limit is equal to x approach to 1 from the left side, x minus 1, which gives us 2. We can plug this in now. So left-hand derivative is 2, right? What about the right-hand derivative? Limit x approach to 1 from the right side, fx minus f1 over x minus 1. We learned this. Let's try to do it faster now. So this is equal to x approach to 1 from the right side, negative x squared plus 2x minus 1. Our f1 is 1 minus 1. This is over x minus 1. What can we do? We need to work with our numerator. 1 from the right side. Let's take it under the x parentheses, negative 1 parentheses, minus 2x plus 1 over x minus 1. I can take the negative 1 out. Negative limit x approach to 1 from the right side. X minus 1 squared over x minus 1. This is x squared, x minus 1 squared, right? So therefore, this limit is equal to negative limit x approach to 1 from the right side, x minus 1, which is equal to 0. So derivative from the right side is equal to 0. But derivative from the left side, our left-hand derivative is equal to 2, our right-hand derivative is equal to 0. So therefore, we will say this function is not differentiable at 1. There is no derivative at 1. This function, do we need to write? Well, let's say this function does not have a derivative at x equals to 1. If x is equal to absolute value of x, does f derivative 0 exist? We need to check the limit, of course. Fx minus f0 over x minus 0. As we said, if there's a value that makes out inside of the absolute value 0, we need to check the limit from the left and right. And let's see the graph of the absolute value of x2. We will need it after solving this. Talk about something like this, right? It's really straight. I can't draw it good. Limit x approaches 0 from the left side. Fx, or let's just go absolute value of x minus absolute value of 0 over x minus 0. Absolute value of x from the left side of it, right? So therefore, this is negative x. Negative x over x is negative 1. So we will say left-hand derivative is negative 1. What about right-hand derivative, right? X approaches 0 from the right. absolute value of x minus absolute value of 0 over x minus 0. Now this absolute value is equal to x, so we can say this limit is 1. Right hand of the derivative is 1. These are not equal, so we will say we do not have a derivative. This function is not differentiable at 0. But if you look at the graph of the function, this is y equals absolute value of x, right? The function is continuous, right? We can clearly see that. The function is continuous everywhere. So we need to understand that just because the function given to us continuous, we cannot talk about derivative of it. If there is sharp turnings like maybe this, these points are not differentiable. Theorem. A is a subset of R, A belongs to A, and f is a function defined from A to R. If the given function f is differentiable at A, it is continuous at A. Now let's try to prove this. First of all, because f, let's write it, because f is differentiable, let's define a gx as fx minus fa over x minus a. Because f is differentiable, when we define the g to be a minus the a, because a cannot be in the domain here, goes to r, there is a limit at point a, right? Because f is differentiable. There is a limit at the point a, even though it's not in the domain, because it makes the denominator 0. And this limit is derivative of fa, right? From this equation, let's try to leave fx alone. Gx times x minus a, I multiplied both sides with x minus a, and now I send fa to the other side, plus fa is equal to fx. Let me try to create some space for myself. Okay, I can read it, right? Yes. Is fx. If I take limits from every side now, as x approaches to a, this will be equal to x approaches to a, gx times x minus a plus fa. If I plug this in, I am seeing that this part is equal to 0. And this limit is equal to fa. So what did I get from here? Limit of fx as x approaches to a is equal to fa. And this is the definition of continuity, right? We talked about these. So therefore, now these 3 dots mean that I came to a conclusion. F is also continuous at A. From this, we will say, if f is not continuous at the point A, it is also not differentiable. Last definition, if a function f defined from A to R is differentiable on A and f derivative is continuous on A, f is called continuously differentiable. Is fx equal to x squared continuously differentiable on R? What is our definition telling us? Is if it's differentiable on A and f derivative is continuous. Let's start with differentiating it then. X approach to A. X squared minus a squared over x minus a by the definition. Fx minus fa over x minus a, plug it in, x squared minus a squared, right? X approach to a, let's write this as x minus a times x plus a over x minus a. Cancel these out, plug it in, 2a. So f derivative a is equal to 2a. If you want to write x instead of a, f derivative x is equal to 2x. So the function given to us is differentiable. Is this continuous on R? Yes, it is, because we know that every polynomial function is continuous on R. So therefore, we can say x squared is continuously differentiable on R. Yes, it is.